So, right, I think I should start. Hi, my name is Sebastian Müller. I'm a student at KIT in Karlsruhe, Germany. So it's about analysis. It's also about automated signal analysis, automated signal reception, or if you want to call it that way, signal intelligence. And what are, first of all, reasons for doing that stuff? So first off, you may want to do spectrum monitoring. For example, in Germany, there's the Bundesnetzagentur, which has to make sure there's no misuse of the spectrum and that everyone stays in their bands. And for this purpose, they need to identify where signals are and what signals are, or where they belong to. Second, it's super cool if you can explore real-world signals, especially when you're a beginner. So, for example, if you want to have a look at an LTE signal and have a look at the frame and where are the pilots and so on, it's very hard to do that if you're not like an expert in that topic. So it would be very cool if everything can be automated, and then beginners can figure out why signals work and why are the parameters chosen that way, and why they maybe wouldn't work otherwise. Also, you can do live modulation. Simplest example would be if you want to listen to a local radio station, you're actually doing live demodulation. And you can do batch processing of several signals. So you don't have to look at one signal because everything is happening in the background, automated. There can be several signal chains that deal each with one signal. So okay, what do we have to do if we want to receive unknown signals? First off, we have to detect them. So the question is, where is the signal located in the spectrum and what's its bandwidth? If we have done that, we need to mix it down into a complex baseband, and then we would do something like filter it, decimate it, to be able to handle the amount of samples. And next, you would start like an iterative cycle of analysis, and then doing a step to demodulation, then analyze again some parameters and so on. And if you did that some time, you will be able to demodulate the signal. And if it's encrypted, you also have to decrypt it. So these are all the tasks that are possible. So what was the workflow before? This is like I did it. Maybe you were a bit smarter than me, but I did something like this. So first off, there is a USRP source. So I just received the signal and dropped it in a QT sink or frequency sink. So I just had a look at the spectrum and look and search where is energy located, because normally energy means there could be a signal. If I have found what I have been looking for, I would assume or estimate by thumb the center frequency and the bandwidth. And I would try to remember that and drop in the next block, which would be the frequency translating FIR filter. This block does everything, including the downmixing, the decimation, and the filtering in the baseband. So I would enter my parameters here, which I found out while looking at the sink, the frequency sink, and I would just write the samples away to a file. Then I would do some analysis, which I have done in MATLAB, I have to admit. And for example, there are other tools like Python, SciPy, or in Spectrum. And I would try to estimate all the parameters that would be necessary to finally demodulate the signal. And for demodulation, I would use gr-radio or other tools like MATLAB or whatever there is, you name it. So this flow graph is not that cool. Why is it not that cool? First off, you have often to stop and adjust the flow graph. Like you have to start it, have a look, estimate some things, stop it again, drop in more blocks, and then fire it up again, and yeah, all do this all in a cycle. You would often, or I at least, would often try to estimate by thumb all the parameters, like, okay, this could be 2.45 gigahertz, I don't know, and hope that it will work out. And yeah, it's not possible to do any real-time analysis with this, because you always have to stop the flow graph. Also, you need much expertise to perform these steps, and it's not possible for a beginner, like a one-click solution. So you have to really know what you are doing if you tried it that way. So, and this is exactly where the inspector comes in, and it tries to make these tasks I just mentioned more easy. And I will now go through the components or the blocks of gr-inspector and tell you what they can do. So first off, we talked about detection. Oops. And if you want to detect a signal, normally we do energy detection. Like, okay, we assume when there's energy in the spectrum, there could be a signal. And this block can do this for one or more signals. And it works either by setting a threshold with the block parameter, or there's also an automatic algorithm that tries to find power jumps in the PSD and interprets them as signal edges. There's also functionality to suppress narrow signals, which helps to avoid false detections. And the output of this block is first the estimated PSD of the input signal, and the second one, as you see, this is a message port. It passes the information about the center frequency and the bandwidth of the detected signals. So next what you would do is you want to visualize what you have estimated. So there's the Qt gr-sync for that, and it just takes the estimated PSD from the block before and plots that in a Qt window. Also, it takes the bandwidths and center frequencies of the detected signals and marks them with edges. Yeah, and next to the markers of each signal, there are also the properties plotted, like center frequency and bandwidth, and there can also be more parameters that I will show on the next slide. And this block also enables manual selection. So if the automatic signal detection messes up because you have a bad SNR, for instance, you can do a drag and drop selection here. And this is a screenshot of how the GUI looks like. So what we see here are three signals in the spectrum. And as you see, the one on the left and the one on the right, they just have their center frequency and bandwidth plotted next to them. The one in the middle has more text. So what's up there? I don't know if you can read it in the backline. So this is an Ofdm signal, and there is an analysis block that feeds the results back to this GUI block. And the results get appended to the text printed next to the markers. So what we can reach here is the center frequency, the bandwidth, but also Ofdm specific parameters like subcarrier spacing, number of subcarriers, cyclic prefix length. So now when we have detected the signals that we want to use, we have to do the downmixing and decimation and filtering. And this is exactly what the signal separator block does. It calculates an FIR filter for every detected signal and applies that in complex baseband. Or you can provide a JSON file with pre-calculated tabs, so to save CPU usage during runtime. The output is a bit complex here. So as you see, it's again a message port. And its format is like, first off, a header that contains the signal information like signal number, center frequency and bandwidth, and then what follows are the complex samples of the signal. Now if we want to process the signal further, we have a problem because there are nearly no blocks that would take my message format here that I chose. So there is the signal extractor. What it does is just it extracts the complex samples of one signal out of this message and passes them again as complex stream, as most GNU radio blocks takes complex stream samples. Yeah, right. Yeah, and also the sample rate of a signal is not known during runtime because it tries to sample following Nyquist criteria. So there is, it depends on the bandwidth of the signal. What's the sampling rate of the signal after the signal separator? And there are applications where you need to know your sample rate exactly, and therefore this block also has the possibility to resample the signal to a well-defined sample rate. So the second bigger topic I dealt with is Ofdm, and there I tried to write an Ofdm estimator, parameter estimator. We have seen the results of this block earlier in the GUI screenshot. And what it does, it estimates the subcarrier spacing, the symbol time, subcarrier number, and cyclic prefix length of an Ofdm signal. And yeah, as I said, the results can be fed back to the Qt gr-inspector sync and will be plotted next to the signal. Also, there's an Ofdm synchronization block. This is surprise, it performs a frequency and timing synchronization for Ofdm signals. And we have also some modulation classification ability. This was not done by me, but by Christopher Richardson, who was a Summer of Code and Space student last year, and he dealt with automatic modulation classification using TensorFlow. So, and now the cow says demo time. So what I want to do now is show you a typical gr-inspector flow graph where we try to listen to a local radio station. So I have my USRP right here. And these are just the blocks I just introduced to you. So here's the USRP source to talk to my USRP here. This can be exchanged by any other source that provides a signal. And then here's the signal detector, the GUI inspector sync. And the results from here will be fed back to the signal separator where all the mixing and downsampling and filtering will be performed. Since we're only listening to one signal, we will extract it here and pass its samples as a complex stream. And what follows then is just a basic FM demodulation chain. So this thing right here is completely GNU radio. So this was here before. And these blocks down here, this is all gr-inspector. So let's fire it up. Okay, it's flashing my FPGA, so I maybe should have done this before. It should only take a few seconds. Okay. So now we see here. Actually, now I have enabled manual detection because I assume the SNR in here is too bad to do anything automatic. As you see, it's pretty noisy. So we have one signal here, and I already have seen at 100 megahertz there is a local radio station here in Bristol. So you can try to listen to that, and I don't think it's quite good printed on the beamer. There are signal edges right here and right here. And I can drag and drop them to adjust the bandwidth of the signal. So let's try this. there's some kind of sweet spot for the bandwidth. Whoop. Maybe add some more gain. Okay, only noise. Oh, no. Okay, I didn't think the SNR would be too bad here, because at my place it worked. So let's try this one more time.
You can try to find the wireless mic.
Yeah, I don't know, but we can try that, yeah. No. So, I don't know, maybe you can hear it a bit. There is some music in the background, but it's super noisy. Okay. A pity. Yeah?
If you touch the antenna, does it get better?
Yeah, you can hear there's some music, maybe. Okay, okay. For the audience and in the stream. Yeah, okay. So, okay, yeah, and that's it. Thank you for your attention. And yeah, we had it earlier about participation and getting started in GNU Radio, and I think Google Summer of Code is a super thing to get started with, like I did. Okay, any questions? Martin, yes?
Was there any particular event that got you into signal intelligence?
Yes, I think. Okay, I know what you want to point out. So yeah, at my university we had the IEEE Signal Intelligence Challenge, and which Martin did bring to life. And yeah, it's all about detecting signals in a known band, but you don't know anything about them. So you have to do the things I just mentioned, like detect error. As I said, started with MATLAB and in Spectrum and such things. And yeah, that's what got me into this kind of topic, and that's why I also applied for GSOC last year, right?
So you wouldn't happen to be on the committee that runs this challenge and is looking for students?
Yeah.
Okay.
Yeah, right.
Can you say a few words? What are you doing in this Ofdm block where you detect?
Yeah, it's so basically there's just an algorithm implemented there from a published paper. And let me think if I can recall what it really does. So,
Some cyclostationary?
yeah, right. It's cyclostationary features, and if you do a fixed length correlation over the time signal, you can find out the used symbol time, I think, and then you can do the cyclostationary analysis, so in frequency domain and in time shift domain, to find the cyclic prefix length. Yeah, so it's just two peak searches in these two directions.
How many seconds of signal do you need to get reliable results?
Concerning which the Ofdm, it's a number of samples that you have to capture, and it's about, I think, in the area of 7,000 samples.
You cannot say it like that. It completely depends on the SNR of the signal.
Right. Yeah. Right. If the SNR is bad, estimation will be bad as well, of course.
You need more samples.
Yeah. Yeah, but I have tested it, and below 7,000 samples, there are no reliable results available.
7,000 modulation, but not high.
Okay. Then I think that's it. Thank you.